Hello, everyone, and welcome to a new session of Gravitículas. Our speaker today is Osvaldo Chandía. Osvaldo received his PhD from Universidad de Chile in 1998. After that, Osvaldo held 3 postdoctoral positions at the UNESP from 1998 to 2000, then at Pontificia Universidad Católica de Chile from 2000 to 2003, and then at Istituto Nazionale di Fisica Nucleare from 2003 to 2004. Then, from 2004 to 2009, he held an associate professor position at Universidad André Feyio. And currently, Osvaldo is an associate professor at the science department at Universidad Adolfo Ibáñez. So we would like to invite Osvaldo now to tell us all about the B-RNS-GSS string. So Osvaldo, please, we are all yours.
Thank you. I don't know if I'm going to say everything about this, but some aspect at least. Well, just to begin, B stands for Berkowitz, RNS for Ramond-Neveu-Schwarz, and GSS for Green-Schwarz and Siegel. Just the names of physicists that contribute to the development of string theory in the last 40 years. Now let me, I can change page. So let me, I don't know what's going on. That's, okay, now, usually people ask for what is the motivation of doing this kind of research. So I have 2 short answers for that. One is the most common one is that string theory provides a unification of particles and interactions, including gravity. So it's something like a quantum theory of gravity, if you want. But other motivation is when you describe some, let me start over. Some gauge theories can be described in terms of string theory language. For example, n=4 super Young units in 4 dimensions can be seen as a special string theory in 10 dimensions. So some people think that it's an alternative description of some field theories can be done in terms of this language. So, so some properties of strings are the following. First, it needs space-time dimension to be bigger than 4, actually to be 10. It needs supersymmetry. There are 5 possible string theories that can be constructed in following certain rules. And the last property I think is important for my discussion is it's necessary to understand the role of a space-time geometry in order to get, for example, something like a 4-dimensional theory from string theory. So probably you have heard about this, but just let me remind you. All the string is a loop that can vibrate and moves in space-time. So the vibration of the string can be interpreted as a elementary particle. And the interactions of nature, for example, gravity interaction mediated by the graviton, can also be seen as a particular vibrational mode of a string, in this case, a closed string. You can see in the pictures, there are 2 types of a string, closed and open. And each of those can be vibrating in different modes. If the string is vibrating in a special mode, will be a graviton, for example, or a photon, or many other states that can be constructed in these theories. If we are dealing with bosonic string, I'm going to review in a moment, we also have the possibility of having a tachyon, a particle with imaginary mass. So in principle, I'm going to the starting point of this model I'm going to describe is RNS. It's a a version of supersymmetric string. But I'm going to start with bosonic string because it's easier to describe the quantum regime. So, so let me summarize this slide. Elementary part. So sorry for the delay. So I was saying that interactions can be seen in strings, like in the way I'm showing in the picture. Two closed strings in this case join to form one closed string and then split into two strings. So as in the middle drawing, I'm showing that exactly this. This reproduces a field theory Feynman and the field theory diagram is that in the second, we had to the interaction points and also propagators. In our case, in the string case, there are no need to include interaction points any time like that, and the propagators also. So that is replaced by summing over different geometries of the worksheet. So in this case, the diagram is showing the equivalent to a 3-level amplitude in Feynman language for field theory. So are you with me?
Yes.
Okay, so now let me review general aspect about the strings. So the first step is that the action to describe the dynamics of a string, we just replace the point particle relativistic action for the analogous to the strings. In this case, in the point particle relativistic particle, sorry, in the relativistic point particle, the action is proportional to the length of the trajectory, the point particle. For the string, the action is proportional to the area of the string. And the string, when it evolves in time, it describes a two-dimensional surface. So if we compute the area of this surface, we say that the action is proportional to that area. Just the size of the string is of order of the Planck length. This alpha prime here is describing so this the tension of the string, but its square root is just it's a size of describe the size of the string. So it's a very tiny string. So for that reason, maybe it's not possible to observe it in a particle accelerator yet, because it's very small. But I'm not going to focus on that, but let me just remind you, I think probably you have seen this before. So if not, just interrupt me. So the action it's useful to write it in this form. Here I had introduced an auxiliary field, which is interpreted as a worksheet metric, a G, small g. And so in such a way that if we integrate out the G, I recover the original expression for the action, the starting point. So now in this language, G can be used to have a geometrical interpretation of the theory, and also to allow us to quantize the theory and get some physical sensitive theory. So the worksheet coordinates are sigma and tau, are collectively called in this index I, and the position of every point of the string can be parameterized by this field X, which is a vector in spacetime. So X is a coordinate of spacetime, the usual spacetime we're used to. And there's a difference between that space and the worksheet space. So please don't confuse those two spaces, although they are related. So in this case, just I'm coupling these X coordinates with the Minkowski metric of the spacetime. This eta is -1. It's a metric of d times d, where only diagonal terms are not zero, and is the usual structure, -1 and plus, +1, +1. So, this next step is to quantize this action and get what is the physical content of the theory. But before that, let me write again the action. So the index M runs from 0 to D. Sorry, I made a mistake here. It's D-1. D is the dimension of a space-time. Ij is just sigma and tau. So the theory is invariant under Poincare transformation of the X field. So as you can see here, but also has local symmetries. There are two sets of local symmetries, of course. One is the symmetry under general coordinate transformation, in which sigma is a vector, sigma and tau are parts of a vector, G is symmetric, and X are a bunch of scalars. Okay, that any theory with local reparametrization will have this kind of symmetry, but in 2 dimensions, remember the worksheet, that is the Weyl transformation, in which G transformed like with a factor, any function of sigma and tau, and the action remains invariant. This is special for 2 dimensions because of this combination of G, the inverse of G, and the square root of the determinant of G. So just in 2 dimensions, you have this kind of symmetry. Now, using these 2 symmetries, we are going to gauge fix the metric to any value we want. Actually, this has to be the case because the original theory doesn't care about, I mean, the starting point doesn't care about any local geometry for the worksheet. The action is just the area of the worksheet. Doesn't matter how you compute that area. So, so in that sense, G is like a gauge field. So, and any gauge field you remember from electromagnetism, for example, is related to a local symmetry. In the case of electromagnetism, that's U1 symmetry, gauge symmetry. In this case, the local symmetry are these 2 set of transformation I'm showing you here. Now, let me go back a little bit. With these 2 local symmetry, I can use the parameter of the symmetry, 2 from sigma and 1 from the Weyl symmetry. I can gauge fix to any value I want the metric, except 0, for example, probably. Remember that G is symmetric, so it has 3 independent components. So this is okay in the classical theory I'm describing here. But if you want to get something like a quantum version of this, you have to discuss this in a quantum regime. So, but before that, so usually it's very wise to gauge fix the worksheet metric to a Minkowski metric. So, yes, so taking that form. So in that form, the action becomes the expression I'm writing there. It's very simple. It's just B is free scalars living in satisfying the dynamics from this action. So free scalars has very simple equations of motion, and everybody can solve that equations of motion. Convenient boundary condition for the fields. But the difference between this system and a bunch of free scalars is that there are constraints. Before gauge fixing, we had the worksheet metric, and the variation of the worksheet metric provide a constraint on the field's axis. In this case, the variation of this metric with respect to G is the stress energy tensor. With this gauge, with this form of the metric, the stress energy tensor is just this one, and the constraint is this constraint. The constraint is that this stress energy tensor has to vanish. So, but as already said, all this is true in the classical theory. If you want to perform quantization, you have to be careful about all these statements. But naively, any constraint will annihilate the physical states of the theory, or better saying that the definition of physical states are those that are annihilated by these constraints. So let me move on to the quantum theory. So instead of describing just the action, we need the path integral representation of this physical system. So in general terms, the path integral of this system is this expression I'm showing here. We have to sum over all x possible configuration for the fields x and all possible configuration of the metric, the worldsheet metric G, with the corresponding exponential of the action. Probably I miss an I here if we're doing Euclidean, or a minus S if I'm doing, I did it wrong. Minkowski's formulation, I forgot to put an I here, or a minus S minus in the Euclidean case. So anyway, so we had to gauge fix the metric in this path integral. That's not so easy. We had to be careful with that. I don't want to spend time on that. Just let me say in words, when G to any, for example, to Minkowski value of the metric, have to be careful with the measure of dg. I have to define this dg. So the way in which dg is defined is such that once one gauge fix g to any value, so the flat metric, for example, now we have to in the process of gauge fixing the metric, we have to put some very specific deltas in the path integral. So the Dirac deltas, and those Dirac deltas are when they are integrated, provide the appearance of a pair of auth variables, Grassmannian ghosts B and C. And now when one fixes the worldsheet metric to the value we want, B and C appears. Now, I'm just saying that this going from here to here is not such easy, but I don't want to spend 10 slides to show that. So in our case, let me note that we are not integrating over G anymore because G is fixed. We are now integrating on a pair of ghosts, that fields that were not present before. Okay, so now let me choose a special metric and a special coordinates because it will be useful later. So instead of using sigma and tau, I'm going to use Z and C bar in these combinations, and the worldsheet metric is flat. So now the action becomes this expression. It's simple, a bunch of free scalars plus a free field Lagrangian for the B and C ghosts. In this, on all the expression I'm going to write from now, every time there's a partial is the derivative respect to Z, and a partial bar is the derivative respect to Z bar. So this theory, when we gauge fix the metric, we lose the original Weil and diffeomorphism invariance, but we are left with a residual local symmetry. This is the local conformal symmetry. So this is the way in which the field X, B, and C transforming under a conformal symmetry. These conformal symmetry transformation are generated by the stress energy tensor, as probably you know. In this case, this is expressed in terms of for X is just this expression, and for the ghost is this the other expression. So I'm calling the part with X matter, and the parts with B and C is the ghost part. Okay, so what is there is one more information necessary to quantize the theory. Besides conformal symmetry is not enough to quantize anything. We have something like the conformal symmetry, but with where epsilon is replaced by for this transformation, epsilon is replaced by C. You cannot see that immediately from the slides, but let me tell you, that's the way. But anyway, the BRST symmetry is generated by this Q here, and this Q here is expressed in terms of the ghost and the matter in this way. This is generic for any theory that has local symmetry and is gauge fixed using the procedure I mentioned here. It's called the Fourier-Popov method, and you get this chart anytime you do that thing. So now, this action is conformal invariant. It has conformal symmetry generated by this, and it has this BRST symmetry. But the BRST symmetry is not just this expression. It's not just conserved. I mean, d bar on this expression is 0. It's also, it satisfies a very important property. It is nilpotent in the sense that if you compute Q squared, it gives 0. That's a requirement for all the theory with gauge symmetry in which you construct a BRST charge. But in the special case of the string theory, Q squared is not 0 for any X field you put here. It has the number of X fields you put in the action has to be 26. So that means the dimension of a space-time is 26. You don't have 26 scalars, you don't have Q squared equals to 0. So in this way, this is a way to see that why string theory needs the dimension of a space-time to be certain value. For the bosonic string I'm reviewing here, that value is 26. Okay? Now, why this? What is the role of this BRST charge? So now, when I have Q squared equals to 0, I can define something which is called the cohomology of Q. That is an equivalence class of states will satisfy Q U equals 0, and anytime you have two states that differs in Q of something, those two states represent the same physical states. So this sounds something like an equivalence class. So in physical term, in physical language, Q U equals 0 is the equations of motion of the state, and delta U equals Q of something is the gauge invariance of the state. So let me, for example, construct the massless state of the bosonic string. It's this expression here. Let me tell you what it is. C is C. So the physical content is encoded in this field. It's a field of X, and it's a vector in terms of in a space-time framework. So when you compute Q on U equals 0, give an equation sets an equation for AM. It turns out to be this equation. I hope you recognize this equation is the Maxwell equation, the derivative of the field strength. On the other hand, the gauge invariance for U gives what is the transformation for A such that two U's represent the same physical state. In this case, if you change AM by AM plus delta AM equals to the derivative of the gauge parameter, then you are describing the same physical states. Given Q gives you all the possible physical states of your theory, of the string theory you are considering. This is not the only state of the theory. There are a tower of massive states. I'm not going to write, and there's also a physical tachyon too. So a tachyon is a particle with imaginary mass. So as far as I know, that's not a good thing to have a particle with that property. So one way we would like to eliminate that kind of tachyon. Okay, but let me, in words, to say what I'm going to show now. I'm going to show you the construction of a BRST chart for theories with supersymmetry. Why supersymmetric? Because I don't want the tachyon. The tachyon has to be eliminated. Once I construct Q, I'm going to show you how to get the physical states. So now, but before that, as I mentioned in the introduction, it could be a good idea to have the string moving not in a space-time, in a flat space-time, but in a curved background, for example, with a background with certain geometry. In the case of bosonic strings, this is easy to implement. Just replace the Minkowski metric by a generic metric. So this theory is classically conformal invariant. You can construct a BRST chart, everything works. But a nice feature of a string theory is that if you do quantum computation of this model, this G is not any metric you want. It's the one that satisfies Einstein equations. Okay, this is not so clear to see it at this level. What I'm going to show you later is in the supersymmetric case, the analog of this action is enough to get the equations of motion for the supersymmetric version of Einstein equations. Okay, let me just mention a phrase about how we are going to incorporate supersymmetry in the model. One way is to do it at the level of space-time. So here every x, the field x, which is the coordinate of every point of the worldsheet, has to have a supersymmetric partner, something like a theta Grassmannian odd variable. Okay, there's a limitation of in what dimension you can do that. So 26 dimension is not possible to construct as a supersymmetry. So for some reason, we had to reduce the space-time dimensionality. And that's going to be the case. Other possibility is to incorporate worldsheet supersymmetry at the level, supersymmetry at the level of the worldsheet. So in that case, the super partner of the X has to be an object which is all, again, Grassmannian odd, but with this label M. Again, we have dx. We are going to need the fermions in the worldsheet action. Okay. So other interesting observation is once we introduce supersymmetry, either way, the tachyon will be eliminated. Okay, because the tachyon is unique. So and probably you know that supersymmetry is a symmetry that relates fermions and bosons. And if the tachyon is unique, there is no possibility to relate it to a fermion. And actually, it's not possible to construct a supersymmetric partner of a a state that has imaginary mass. So now I'm going to move to supersymmetry. I'm going to, I'm sorry for this, that's very not nice to see, but anyway. I'm going to describe the Ramond-Neveu-Schwarz string first. What is the logic here? Is for every field, in this case, X, we add a partner, a supersymmetric partner. In this case, dx are related with d psi m. This psi m are odd Grassmannian. I mean, it's a Grassmannian odd variable. They are coupled in the same way between them, between them or among them with the Minkowski metric. The same Minkowski metric is here. And if you remember, for the bosonic string case, we had ghosts, which those ghosts were Grassmannian odd. But now we need their supersymmetric partner will be Grassmannian even. They are turns out to be these beta gamma fields I added to the action. So this is the R&S action in the conformal gauge. Okay, just like in the bosonic string, this has to be complemented with constraints. Those constraints are just, again, the stress energy tensor appears, but the supersymmetric partner of the stress energy tensor, which I'm calling G, is also a constraint of the theory. So we have these two constraints has to annihilate physical states. So the way in which implemented this annihilation on physical states is first construct the VST charge and then show it is nilpotent and finally construct physical state. So R&S BST charge has this structure. It's always the same type of construction. If you have matter and ghost generators, you construct the BST charge as the integral of C times ghosts times the matter part of the generator plus 1/2 the contribution from the ghosts. In this case, we have mat T and G, the stress energy tensor and the supersymmetric and its supersymmetric partner. So we have two terms, C for T's and gamma for G in this combination. So and it's not so difficult to show that this charge is nilpotent only when the dimension of the space-time is 10. This is good news because in 10 dimensions, it is possible to have supersymmetry. So supersymmetry is not an abstraction of the theory. We can construct, quantize the theory with supersymmetry. So I'm not going to construct the states because it's not had to go step by step. I mean, state by state and checking if those states are physical by being annihilated by this Q. Instead, I'm going to just move on and discuss what is the problem with the space-time supersymmetry in the R&S string. So the problem is, I hope you see that here we don't have a space-time supersymmetry. Where are the space-time fermions? Where are the states with space-time supersymmetry? It's not visible. So the reason why it's not visible is because space-time supersymmetry is not manifest in R&S. So let me recall you what do I mean by supersymmetry. In 10 dimensions, supersymmetry is realized in terms of coordinates x and theta. Those transform under supersymmetry in this way. Theta is just a shift. and X transformed in this way. Gamma here is the 16 times 16 symmetric gamma matrices in 10 dimensions. So this is generated by certain charge. This charge satisfies certain algebra. And supersymmetry algebra is part of the supersymmetry algebra is this one. You take two supercharges. The commutator between two supercharges is gamma times the translation operator. In string theory, I just show you, the translation operation is just the integral of dx. So a natural question is, what is Q? How to construct Q? And this is a hard stuff to do. It was done by Frida Martinek-Schenker in the 80s, and it involves a series of steps that are not possible to generalize to any background. It works for background, for space-time with certain properties. For example, and space-time that satisfies those properties is Minkowski space-time. So in flat space, what do? We take the temp size. Remember, we are in 10 dimensions, and instead of working with size, we work with this 10 combination of size. Here I'm introducing sigmas. Sigmas are bosons. So what are we doing here? We are doing a bosonization of the psis. These sigmas satisfy certain algebra. They commute between them. For example, sigma 0 with sigma 0 is something, the commutator of sigma with itself is proportional to 1. And the same for sigma 1, sigma 2, up to sigma 4. But the commutator between sigma 0 and sigma 1 is 0. Okay? That's not the only thing we have to do. We also need to fermionize the bosonic cost. This is very tricky. Instead of working with beta and gamma, we work with phi and a pair of fermions eta and psi in this way. Okay, so all this is necessary to construct Q. Q turns out to be equal to this expression here. Needs a factor of the phi, we find it here, and needs a special combination of the sigmas of this way. I didn't mention, but no, I mentioned that we have 16 of these Qs. So this plus minus here are such that we have 16 of these Qs. So I think that it's up to a convention, but we have to impose, for example, that we have an odd number of plus here. We are allowed to an odd number of plus in order to get 16 Qs. Okay, this combination of sigmas is called spin field. So I'm going to call it sigma alpha. Now compute the algebra and see what happens. So unfortunately, when you compute the algebra, you don't get the momentum. You get this expression. This is not the generator of space-time translation. It's not the momentum. But this is very tricky. It's related to dx, so the generator of space-time translations, by a special operation with the name of picture. I'm going to define them in a minute. But beside that, you see that this construction is very special for a flat background. If I want to a different background, for example, the background, it's not possible to do this. So for that reason, the description of backgrounds with the description of backgrounds with supersymmetric invariance is not so easy and sometimes impossible using the RNS formalism. For that reason, many people prefer to work with a different formalism in which space-time supersymmetry is manifest. So that means we start with x and theta as fundamental variables and try to quantize the system. But I'm not going to follow that route because that would lead me to Green-Schwarz and eventually pure spinor formalism, but I'm not going in that path today. I'm going to continue to describe RNS and try to do something in RNS to make supersymmetry manifest. In other words, find a way to define Qs. This is little Qs to get this algebra correct. Okay. Now, I think sorry, this is. So now I'm going to define picture. Picture is just you can define this integral here. And for example, an state that includes a factor of e to the pi phi turns out to have picture equal to p, where picture operator is. So now note that, okay. Let me go. So I was at this point. You see here, this expression, this operator has picture -1, and the generator of space-time translation doesn't have a factor of e to the phi, so it has picture 0. So there's a chance to relate these two operators by picture changing. But the construction starts forward in the following way. We define a picture changing operator by this, the VST transformation of the fermion psi, and the important property is that if a physical state V with certain picture P, I mean certain B has picture P and it's physical, I mean that means by Q, then ZV is also physical and but has picture P+1. So when you have a physical state, you can choose what picture will have. So for example, construct the vertex for the photon. There are many states you can construct from B applying Z that also describe the photon. So in particular, this combination of E and psi, when Z acts on it, gives you exactly what we expect, the generator of momentum, the integral of the momentum, the integrand in the momentum operator. So in RNS, we have supersymmetry algebra, but it closes in this way, not in the way we like. In that sense, we are satisfying the supersymmetry algebra up to this picture, but it's only if this construction is valid on shell. That means the states V you are considering has to be annihilated by Q. They has to satisfy the equations of motion. So what Berkowitz noticed last year is that we can extend this the RNS formalism to redefine the VST charge in order to implement the supersymmetry algebra without using picture. So, and the situation is the following. Instead of having QRNS as VST charge, we just used this combination. So why is the integral of eta relevant? First, eta is a fermion, so it squares to 0 trivially. It also commutes with QRNS such that Q squared is 0 now. So this is a good term to construct an nilpotent charge. A different interesting feature of this integrand is that if you remember a couple of slides before, when we introduced phi, c, and eta, we did this transformation. If you see that c appears as the derivative of xi, sorry. So the zero mod of xi doesn't appear. So any physical state we construct from involving beta and gamma will never include the zero mod of psi. So that means that if I act the integrand of eta, what measure is if any state has or doesn't have zero mod of psi. So if it has, then the condition of being annihilated by this combination implies that it's not physical. So only states which are independent of the zero mod of psi are going to be physical, which is consistent with the previous slide. It doesn't matter the distinction between large and small Hilbert space. But the main properties, we are going to allow zero mod of psi's, but state annihilated by Q remove that possibility. All the states that depends on the zero mod of psi are not going to be physical. So now, the picture changing operation on a physical state B is this expression. In terms of Q, the new Q is reproduced as B plus Q of something. B plus Q of something is a B-RNS transformation. So in words, picture changing operation is replaced by a gauge transformation, a B-RNS gauge transformation for this new Q. So now, how to construct the generator of supersymmetry is we add to the original RNS construction involving a spin field a trivial term. So this new Q involves the old Q plus a trivial operation. So now you have to find this guy here, construct Q in such a way that you have this now the supersymmetry algebra. If you can do that, then supersymmetry in this formalism will be manifest, and in particular the supersymmetry algebra will be satisfied. I don't know if, so now the next task is how to construct this Q in such a way that all this is true. So now that is the B-RNS-GSS formalism that Nathan Berkowitz invented a year ago. So there are two steps. First, the worksheet action will be the same action as RNS, but we need to add auxiliary fields. In this case, we add theta and its momentum, and theta is the superspace coordinate, and also we need lambda and W, a bosonic, something like bosonic superpartner of P and thetas. So I think I don't have too much time, but maybe I could show up a couple of slides more. So the details are not relevant now, but let me show you that we can construct the Q, the Versti charge, and it has this form. Not so illuminated, but involves almost the same structure as the RNS Versti charge. Involves the spin fields explicitly. In RNS formalism, we don't have this kind of term in the Versti charge, but also need contribution from the new variables. So the new variables appear in this way. So let me tell you that why this makes the theory supersymmetric, manifestly supersymmetric. So every time you don't have X and theta isolate. They always appear in special combinations. In what combination? In this combination. P and theta and X mixed with in this way to form D alpha or pi m. These two fields are supersymmetric. If you transform P in a certain way, you can show that D is invariant, the same for pi. So, and the diversity chart depends explicitly on this combination. Yeah, this is a comment almost for myself. Just this expression, this term here is a reminiscent from the pure spinor formalism, but I'm not going to mention nothing more than that. So now, let me just, do I have something like 3 minutes?
Yeah, of course, no problem.
Okay, so now let me just show you how the physical states appears in this theory. So it's very interesting because first, it's manifest in the sense that all the physical states will be superfields in some are functions of x and theta. So I'm just showing you the first two terms of the massless case. It involves lambda and a superfield A alpha, gamma psi with a superfield AM. So the nice thing is the Beers-T transformation, the gauge invariance, implies that, for example, this AM transform like the gauge symmetry again. So this looks like a photon, not yet, but in a minute it will be. And A alpha transform like this. This capital D is nothing more than the supersymmetric invariant generalization of the derivative respect to theta. This is the definition. But in some way, in the space-time superspace description of super Maxwell, A alpha is a constraint field. So the constraint comes from Q equals to 0. And the constraint equation is this one. So there's a relation between A alpha, AM, and all the superfields I'm not showing you. And the basic equation is this one. It's the symmetrization of the derivative of D on A has to be proportional to the field AM with the factor of proportionality being the gamma matrix in 10 dimensions. So one more step here. This implies that the derivative of all these superfields will be related to each other. For example, the derivative of AM is related to A alpha in this way and defines a new superfield with this index structure. Turns out that this AM satisfies again the equations of motion of Maxwell. You can see that. And the super partner satisfies the Dirac equation, the massless Dirac equation. So if we can expand these superfields in terms of x and theta, we perform an expansion in theta. The expansion in theta tells us that the first term for AM is the photon, and the first term for phi beta is the photon. So this can be repeated to get supergravity, to get massive state, etc. So this is just, and there's no possibility to get a tachyon in the formalism because it's not possible to incorporate a scalar field with imaginary mass in superspace. Okay, this is going to be my last transparency. What is my contribution to this? Is implement this new formalism in curved space. So it's not direct, but I mean, instead of having the x and theta, we have super coordinates in superspace, and less working in similar models taught us that the Wilbine, the superspace appears naturally in this description, and the super connections, the connection for supergravity, also appears naturally in the formalism with this kind of couples. The question is, okay, given that, question, is it possible to construct a nilpotent chart? Well, the question is yes. And there are two requirements. First one is, Q has to be nilpotent and J has to be conserved, so has to be holomorphic. Just one phrase and finish. Remember that in bosonic string, we have something like this. And I said that G has to satisfy certain equations, but those equations come from doing quantum mechanics of the action. In this case, I'm not doing nothing quantum. I'm just computing the algebra, the Poisson algebra to get Q squared to 0, and the equations of motion to get del var J equal to 0. I'm going to not don't look at the result, but when Q squared is 0, it provides constraints on the geometry, and those constraints are expressed in terms of the torsion and Carl Ramond H curvature. So torsion is something like the torsion in general relativity. Just the difference is in superspace, we have this spatial structure. All supergravity constraints involve the component of TA in alpha beta being proportional to the gamma matrix, and we obtain that constraint by imposing Q squared to 0. So I'm sorry not to go into details. I don't want to bother you so much with that. So, but let me conclude. So this new string has elements of RNS that I show you in some detail, and it's also related to Green-Schwarz. I didn't show you at all, but it's nice. It can be done in flat space-time and also in curved background. It could be very interesting to repeat the calculation for backgrounds like ADS times cos 5. Also discuss the possibility of have corrections to supergravity. We know that string theory is not well. It's a theory that corrects supergravity, because supergravity is not a renormalizable theory. Also, some words on compactification can be done in these formalisms. In particular, what is the geometry that of the compact part of the space-time has to satisfy. That's it. I'm going to stop sharing. Are you there?
Yes, of course. Okay, so thank you very much, Osvaldo. It was a wonderful talk. Please, does anyone have any questions for Osvaldo?
Was it too complicated?
Yeah, it was complicated, at least for me, yes.
I'm sorry.
No. I have some questions, actually very simple ones.
Dale.
So in slide 7,
okay.
You showed like the parallel between the typical Feynman diagram and a string theory diagram. I have seen this before. So if you have a higher order corrections, would that mean like holes there?
Something like in the closed string case, this is like a cylinder, right? So now instead of having a cylinder, you put something like a hole,
like a donut hole.
Donut, yeah. So
okay.
That the donut or torus geometry is related to a one loop diagram in the Feynman field theory.
Okay, thanks. And I have one.
Just let me say something more.
Okay.
This decoupling between the difference between tree level and one loop in a string is weighted by a field of the theory. So you don't have to put the couplings in by hand. The theory provides you with the couplings. So,
okay.
Thank you.
And on slide 15, you mentioned this like two supersymmetry possibilities.
This one? Yes.
So actually in your last slides I was lost, but at this point I was still following you. So what's the difference between the worldsheet supersymmetry and the space-time supersymmetry?
Let me say this. This is X is the field, okay? The bosonic string. So what do we do with it to get supersymmetry? You can do it in two ways. One, add a superpartner on the worldsheet. So every X has a psi companion. So you have 10X, you are going to have 10 psis.
Mm-hmm.
Now, that is doing including supersymmetry at the worldsheet level. Now, if you want to do it in space-time, it's a different story, because in 10 dimensions, X doesn't have 10 superpartners, it has 32 superpartners. So because in 10 dimensions, the supersymmetry superspace has 10 bosonic coordinates and 32 fermionic coordinates. Those 32 can be split in two sets, 16 plus 16. I'm only taking one of the 16 to construct space-time supersymmetry. That's, people call that n equals 1 supersymmetry in 10 dimensions. If you add 32, you are doing n equals 2 supersymmetry in 10 dimensions. Did I answer?
Yes, I think yes.
Thank you.
So, Osvaldo,
yes,
I'm a foreign to the topic of string theory, so forgive me for my general question, but I want to the opportunity. So, alongside supersymmetry, which is of course, I think, a key concept, a key theory, a key ingredient in your model and string theory in general. So is there any other experimental observation for your model or in string theory in general that
I would say
you would say
extra dimensions
for
extra dimensions,
higher dimensions?
We need 10 dimensions.
Yeah,
I'm sorry for that. So if an experiment can show that the world has more than 4 dimensions, would be great.
Okay.
Even in the case that we never find extra dimension and we never find supersymmetry, the string theory can be used as a tool to define field theories.
Oh.
Okay? Something like a mathematical tools, a mathematical tool to define a field theory. For example, instead of having the classical example is n equals 4 super Yang-Mills in 4 dimensions. You can write an action and try to quantize that action in terms of in field theory language. A different way to see it is, okay, this system is equivalent to a string.
Yeah,
it's a mathematical invention. So everything you do in that model, you can reproduce it in the field theory. So sometimes it's easier to compute things in the string, but it doesn't mean that the string is physically real, measurable. It's just a tool. You see it?
Yes.
Okay, so that's my answer.
Perfect. Thank you very much. Anyone else? Okay, I think we are in time, but it was very good. So thank you again, Osvaldo, for the talk.
I'm sorry for the connection. Yeah. I don't know what's going on here.
Don't worry at all. That's not your problem. It's an internet connection. We all have those problems lately. Okay. So thank you very much, everyone, as well. And we will see each other, hopefully, on the next seminar. So thank you, Osvaldo. Bye. Bye, everyone.
Yeah, Osvaldo.
Bye.
Ciao.
Bye-bye. Thank you.
Gracias, nos vemos.
Ciao.